Thank you all so much for being here at another computational medicine seminar series. Today we have Professor Johann Guilleminot. He is the Paul Ruffin Scarborough Associate Professor of Engineering and Associate Professor of Civil and Environmental Engineering at Duke University with a secondary appointment in the Department of Mechanical Engineering and Material Science. Dr. Guilleminot research activities focus on computational multiscale mechanics and stochastic modeling for uncertainty quantification. He has received various awards, including student awards, the French Early Career Award, and the NSF Career Award. So with that, take it away. Thank you.
All right. Thank you. Can you all hear me loud and clear? All right. Well, thank you so much, first of all, for the opportunity to present some of our work. Today I'd like to talk a little bit about what we do when it comes to integrating stochasticity in computational methods for personalized medicine. First of all, you're going to see my face and hear my voice, but this is, of course, a team research effort. I would like to show pictures of my group, Senu, who is an undergrad at Duke, and Ginny, Ariana, Shanshan, Pei, Ao, and Alexander, who are graduate students, PhD students at Duke. So I'd like to start by just discussing a little bit the challenges that we are facing when it comes to computational medicine from a standpoint of computational mechanics. And I have like 3 slides to kind of summarize what I would like to talk about. The first thing is the need to integrate patient-specific physical parameters. So if you think about mechanics of the arterial wall, we all know, I guess, in this audience that the arterial wall is composed of 3 layers. So those layers are anisotropic and strongly nonlinear. But in the context of this presentation, I would like to discuss the fact that basically when you run like a bunch of mechanical tests on those tissues, they're showing a lot of stochasticity in them. So if you look at those figures, those are part of a well-known experimental database that was produced almost 20 years ago, where essentially the harvested layers and basically tested the layers in 2 different directions, the circumferential direction and the longitudinal direction. And they integrated like 13 patients. So what you see when you look at those figures, you see essentially 2 things. Well, 3 things. The first one is like you see that it's obviously like a highly nonlinear behavior. Then you see that if you compare the figure from the left and the figure on the right, that they are anisotropic, because you see that this response is essentially much stiffer than this one. But you also see that there is huge variability in it. Like if you look, for instance, on the figure on the left, if you fix like a given stress, you see that the stretch that the material will undergo can vary like from like 20% to 40%. So there is a huge variability in the data we are facing. And that's something we would like to take care of in the modeling we're going to do. The second aspect I'd like to introduce, and this is, I guess, the most commonly integrated aspect in computational medicine, is the fact that we are dealing with patient-specific complex geometries. So here I'm just showing 3 types of applications we have been dealing with. On the left, you have the interface between the CSF and the gray matter. That's a data set provided by Duke. This is a meshed view of the artery wall, and that's something I'm going to discuss quite extensively in this presentation, and that's taken from a database, online database. And this one is patient-specific rib cage, which is also coming from the Duke Hospital. So if you look at those pictures, the geometry is very complex. And the way we assess that, usually when you do computation, is that you say, well, I will have to mesh it. Well, when it comes to doing uncertainty quantification and model things on that, there is another layer of complexity, which is essentially that you need to define a field on geometries which are defined by manifolds. And this is what you see right here. So that's another challenge we're gonna address in this talk. The important thing I would like to say here is that when it comes to computational personalized or patient-specific simulations, we usually mean like we're going to integrate the geometry, because that's something we can essentially get from the hospital. That's something you can get. And in this talk, I would like essentially to also introduce variability in the material parameters. So instead of just doing this and just spending time meshing this, I would like to combine this with that. So when it comes to modeling those things, there are very few uncertainties in the way you can model the geometry because it's essentially a reconstruction error. But when it comes to material uncertainties, you need to account for the fact that basically, if you look at this group of individuals that are just like different people, different ages, different genders, health conditions, there is substantial variability in it. And the last thing I would like to talk about is basically when it comes to running computations, at the end of the day, we want to make sure that the computer is essentially going to return like a meaningful prediction, right? So if you want to do that, you need to account for constraints that are arising from the mathematical analysis of the equations you are trying to solve. So I'm not going to discuss this extensively, but for those of you who are familiar with the mechanics of soft tissues, that's probably a book that you had on your desk at some point. And essentially, what I would like to show you, like if you look on the right, what you're going to see that essentially this is an existence theorem. But to make a long story short, you need to satisfy a set of properties just to make sure that you have the existence of minimizers in your computations. Okay, so that's something we would like to do. So this talk is gonna discuss how we basically address those three topics all at once. And that's something that is gonna basically raise like a few new challenges. I think it's fairly easy to take a geometry and mesh it, right? It's fairly easy to account for this, or it's fairly easy to do that in a deterministic way. But it's more complicated essentially to blend all those constraints in a single computationally efficient framework, and that's what I'm gonna discuss today. Okay, so I'm just gonna formalize things a little bit so that we agree on the terminology and what I'm gonna do. So I'm assuming that I want to make a prediction. So I have a deterministic model that is gonna take P. So P is my input. I have some given operator that would be, in this case, a boundary variable problem like linear elasticity or nonlinear elasticity. That could be fluid mechanics like Navier-Stokes equation if you'd like. And Y is the output. In this presentation, I'm going to focus on something that is called the parametric setting. So I'm going essentially to focus on the case where the input P is stochastic. And this is justified by the fact that I will have to deal with physical properties which are highly stochastic by nature. Okay. So based on the discussion, based on the picture that I've shown you, again, to make things a little bit more concrete, I'm going to model my input as a random field, P, which is vector valued, indexed by omega. So omega would basically be the domain over which I'm trying to simulate my stuff, so the brain interface, this artery wall or the ribcage. And if I'm trying to translate what I said into mathematical constraints, this is to say that P is going to take values in a set S, which is a subset of that Euclidean space. And that space will be constrained either by the physics due to anisotropy or from the mathematics, just looking at the constraints that the model has to satisfy to make sure that my computation is essentially returning something that is meaningful. The second aspect is that omega, which is a space indexing my random field, is a constrained geometry. In this case, I'm going to assume that this is a smooth manifold embedded in the 3D Euclidean space. So really, mathematically, the practical applications would basically comes down to this, like how do I model P on that space and with an omega that is itself a constrained set. Before I do that, I would like to motivate a little bit of the mathematics I'm going to do just to justify what it's absolutely necessary. And so to do that, I'm going to use like a very basic example. So this is like high school physics. If you take like a spring type system, so you have K is the stiffness, U is the displacement, and F is the force that you apply. And what I'm going to do with that, I'm going to assume that I can produce a bunch of springs and I can test them. So I can test them, let's say 100 times. Okay, I have time to do this. And whenever I test this, my stiffness is going to be slightly different. So I have stochasticity in my very simple 1D problem. When I do that, and if I look at the data, one reflex most people have would be to say, well, you know, that really looks like a Gaussian distribution. So I'm going to go with a Gaussian model to model this K. So I'm going to take this deterministic equation. I'm just going to randomize it. So this small k will become this blue capital K, stochastic. U will become the stochastic output, so it's a capital U, and F is deterministic. And so I'm going to assume that K has some Gaussian distribution. And the question I'd like to ask is that model valid? Can I even work with that? So if you assume this, you can calibrate your model and you can run like computations. So if you just focus on the figure on the left, on this horizontal axis, this is essentially the variability of my input. And what you have on this vertical axis is the variability of my output. So what you see is that, well, my response makes sense because when I put more stochasticity in the system, I have more stochasticity in the output. And moreover, if you look at the magnitude of this second order moment, it looks reasonable. So if you just rely on that, the fact that you can run your computations, the model is okay, and you can actually publish something like this. Now, if you are a little bit more careful about the analysis, and you say, well, when I did that, I was working with, let's say, a batch of 1,000 samples, and this is what I get, then you remember your statistics class, and you say, well, you know, there is a bias when you have very few samples. So I'm just going to increase the number of samples I am integrating in my simulation. And what you realize if you do that is basically that this quantity that just looked fine when you work with 1,000 samples starts to essentially blow away, right? You basically tend to infinity. And actually mathematically, because this model is analytical, you can compute the integral by hand, and you will realize that the second order moment of your output is infinity, which is not consistent because you have a closed physical system. You put a finite amount of stochasticity of energy, and then basically you are saying that you are generating infinite variations. The other thing I'd like to say is that in this case, I can do that because the system is very small. But if you think about the model we're going to solve and the model I'm going to show you today, you cannot do that analytically, right? So you cannot access this. So you cannot even compute that. And you cannot reach that number of samples. Like if you have a large-scale computational model that would take a couple of hours to run on a supercomputer, you're not going to say, well, I'm going to run 1,000,000 times my computation. It's just not an option. So you will never realize, if you basically take this simple example, and if you basically apply the same line of reasoning, you will never be able to realize that what you are doing is wrong. So the conclusion of this is that, and in particular now where everything has to be data-driven somehow, well, you can have a model that is going to fit your data. It's going to run, like if you run this, you just take a Gaussian model. Your model is always going to run. It's going to just return your number. No warning sign, and yet the model is wrong. Okay? So the point I want to make here is that you really need to take a look at this, and then you look at your data, and then you integrate the geometry. You should never build a model only based on data if you really want to run computations, okay? All right. So this is the first part of the presentation. So I'm going to basically provide you with an overview of, you know, the mathematical tools and ingredients we are using. I'm going to deliver like a high-level presentation. If you have like any specific question, I'm more than happy to take like questions. But essentially, we're going to need 4 ingredients to do what we want to do. We will need to introduce something that I call an algebraic decomposition. And I will clarify what I mean by this. We need to have a sound way to build probability measures. We need to have a way to sample fields on a complex geometry. for non-Gaussian measures. So again, I'm not going to discuss in details, but just give you those examples, and then I will apply this to the case of soft tissues, human arteries. So the first ingredient is all about ensuring admissibility. And to do that, we're going to use something that I call an algebraic decomposition, which is essentially a way to build your model such that it's going to encode the structure that you need. For instance, if you remember your class in linear algebra, if you are dealing with asymmetric symmetric matrices, one way to ensure that your matrix, your outcome is going to be symmetric is that you can decompose it in a Cholesky decomposition. And then regardless of what you do in your Cholesky decomposition, when you take it and you map it onto the product, then your result is going to be symmetric, right? So I'm going to use kind of the same ideas in a way that is adapted to what I'm trying to solve. But that's the idea. And the goal is really to ensure that well-posedness, and also to provide some flexibility in terms of the physical modeling. This decomposition is really application dependent. So whether you deal with Navier-Stokes or linear elasticity or nonlinear elasticity, is going to change essentially how it's going to look like. So this is the reason why I'm not going to propose you like a catalog of the stuff, but I'm going to show you exactly how it looks like for the blood vessels. But the key questions you need to ask is basically what P must satisfy to ensure well-posedness. So does it have to be bounded? Does it have to satisfy some coercivity, property? And now if I go back to that slide, I don't know if you can read that, but basically if you look at point number C, there is this coerciveness requirement. So right away, you know that, okay, if I want to work with human arteries, I need somehow to know what coercivity means. I need to basically essentially understand how this is going to constrain the model I'm going to build. All right. Then what is a proper state space? And then what modeling capabilities do I need? And that's really something that I would like to emphasize, because you can sophisticate the model as much as you want. We can do mathematics, we can do fancy stuff. But at the end of the day, your model is going to be connected to data, and you're trying to make prediction for decision making. So if I build the most generic class of models, but I cannot identify it because I need a lot of data, then the model is useless, okay? There is always a trade-off between the complexity of what the model can achieve, the fact that you need to identify this. The only compromise you cannot make is about admissibility, about the well-posedness, okay? So this is the first ingredient. The second ingredient is how do we build prior models? And to understand that, I would like to get back to this slide and essentially assume that you know what coercivity means. Again, depending on your background, you may not know this, but assume that you have some information on this. The question is, how do I take this information and translate it into something that I can use to build my probability distribution? There are a couple of ways to do that. In what we do, we use the context of information theory. And within information theory, there is a principle which is very useful, which is called the principle of maximum entropy, which was stated by James about like 70 years ago. And the idea is very simple. The idea is that you have some information and you have a possibly infinite number of models that would satisfy those properties. And this principle tells you that the model you should pick up is basically the model that is consistent with the information that you have, but also maximizes the uncertainties on the information that you don't have. So this is summarized in in this sentence. The maximum entropy distribution is uniquely determined as the one which is maximally concomital, non-concomital with respect to missing information. So I'm not accounting for something that I don't know, but in the same time, I am using the information that I have, okay? So mathematically, this is to say that the density function you are trying to build is an element of a function space, which is a subset of the space of integrable function with positive values that has the largest entropy. And more precisely, if you can write down your equations, if you know stuff on P and you can write your equations like that, then the maximum entropy principle tells you exactly how your PDF is going to look like. If I give you this, then you can tell me right away that this is a density that I have to use, okay? There is something I'd like to say about this expression. So those brackets, this is just a standard notation for the inner product in the Euclidean space. But if you look at this, the structure of this PDF, if you had a class in statistics or probability, you realize that if the information that is basically included in my model in those G's do not mix information on the components of P, then my density will have a separable structure and I will end up with independent components. So in other words, if I know something about P1 and I know something about P2, then the density is gonna yield two independent P1 and P2. But if I know something that is gonna mix information, I know something about the product, then I'm gonna introduce statistical dependencies. Now, the way I'm gonna use it, because remember, the goal is that I want to model stuff like that, like P, okay, that are going to model this on that. So to do that, I'm gonna construct a subclass of non-Gaussian random fields, and I'm gonna write P as this. So P, and that's a definition, right? I'm gonna say that P is some transformation H acting on some latent Gaussian field Xi. So this guy is gonna have a Gaussian distribution, and this guy is going to basically ensure admissibility. So when I do that, this H is going to take care of the well-posedness requirements. And the way I'm going to define this Xi is going to take care of the complexity of the geometry. And I'm going to show you how we do that, okay? But the message here is that we're going to split the construction into two different ingredients. And we essentially build H such that the distribution of P of X when X is fixed is essentially the maximum entropy distribution. The third ingredient that I'd like to use is a sampling technique that is called the Ito-stochastic differential equation, or in mathematics, it's a Langevin equation. And this is essentially, if you remember your class, you had like at an undergrad, like an ODE class. This is basically an ODE that has on top of it like a driving stochastic source, which is coming from this Wiener process, the Brownian motion. So I don't want to comment too much on this because, again, depending on your background, it might just not be relevant. But the point I would like to make is that you have an equation that depends on time, and you're going to integrate it. So I'm going to combine this with a time integrator. So I'm going to discretize time, and I'm going to integrate this to generate sample path. Now, the key thing is like basically, if you define the gradient of this V, so V is called the potential function in this setting. If you define the V like this, then the Q, once you reach the stationary regime, is going to have this distribution, okay, P of Q. So in other words, if I know exactly the density function I would like to sample from, I just take this V, plug it back into this equation, and I integrate. So it's really like an MCMC technique, except that there is no rejection in this algorithm, okay? Now, if you remember what I've just shown to you, if you compare this equation with that equation, you should realize, although it might be complicated because I'm going back and forth, but you quickly realize that if you have a maximum entropy distribution, you have built, based on the information that you had, you can define V like this. And once you have defined V like this, you can plug it back. And it's just a way to sample from your maximum entropy distribution. The fourth ingredient I'd like to introduce is basically how do we take care of this? How do we account for the fact that this geometry is very complicated? And I want to do that on the fly. I don't want to, every time I get new data from a patient, I don't want to spend time building my model. I want the computational setting to account for this on the fly. So the way we do that is that we are considering this implicit definition of the Gaussian stochastic processes or fields. Usually, if you have like a Gaussian random field, if the field is centered, it is uniquely defined by the covariance function. It is going to define the covariance between 2 points on your domain. Now, the issue is that when you deal with patient-specific geometries, you cannot really define the covariance function because the geometry is so complicated that you really don't want to do that. So one way to bypass this is essentially, instead of defining psi explicitly through the covariance function, I'm going to define it implicitly by defining this psi as a solution of this equation. So that's a fractional stochastic partial differential equation. It's fractional because in principle, alpha could be anything. In practice, usually we don't do that for a couple of reasons. But alpha could be anything. So if alpha is anything, that becomes a fractional operator. But essentially, this guy is the normalized Gaussian white noise. So if you solve this equation, this guy is going to have a particular covariance function. So what I'm going to do is that I'm going to introduce some anisotropy in this kernel, and I'm going to play with this guy. So this guy is essentially going to control the white noise. So if you don't like the mathematics description of it, I have a very simple example. Assume that you want to vacuum your carpet. Okay, so you go back home, you want to take your vacuum cleaner and you want to clean your carpet. So, and assume that you have your dog or a pot of flower right in the middle of your room. So you take your vacuum cleaner, you start going, and as you reach your dog, you're going to go around it, right? You're not going to pass over your dog. And then if you look back, your fibers on your carpet that has this somehow completely stochastic orientation, now they're going to follow the path of your vacuum, right? So you have basically filtered this noise in such a way that it's going to look like it's going to follow your geometry. Well, I'm going to do exactly the same thing. That operator is going to define mathematically my vacuum, and my geometry is going to introduce dogs I want to go around. And I'm going to show you how it looks like. You're going to see that it's actually a very nice, very powerful setting to do that on the fly. So there are essentially two benefits doing this. One is that you can define in simple non-stationary field on complex geometries really on the fly. You send me your STL file, I mesh it, I generate it. And it's also very easy to solve through a Galerkin projection. So now I have introduced those ingredients, the basic versions of them. Now I'd like to show how it works in practice, and you're gonna see that it's gonna deliver pretty nice results. So I'm gonna focus on the continuum mechanics background first. So in hyperelasticity, if you are working on the mechanics of arteries, usually we are using strain energy density functions that will look like this. So this is basically the constitutive model. And so if you take the derivative of this guy with respect to the deformation gradient, that's your Piola-Kirchhoff stress. And so usually one of the most commonly employed model is this one, where you have this isotropic contribution that's called a Monet-Rivlin contribution. This C bar is essentially the isochoric version of the right Cauchy-Green tensor, which is itself a function of the deformation gradient. This guy is a penalty term that we use in numerics to ensure the incompressibility of the material. And this guy is basically the anisotropic contributions in the fibers. So essentially, each layer is going to have collagen fibers in two principal directions. That's why you are summing up from 1 to 2. It's really very much like a composite material. And this contribution is going to kick in only when you are stressing in tension. So I'm going to assume that this is a model that works, and I'm going to build a stochastic counterpart of this. So now, if you kind of remember the ingredients, the first step I want to do that I want to make sure that it's going to work. So I'm going to make sure that this is a polyconvex function, and I want to make sure that it's going to satisfy a uniform coercivity property almost surely. So almost surely in probability means that it comes with probability 1, meaning like every time I'm going to draw a sample of my field, it's going to satisfy the properties that I want. Then I move on to the first ingredients. Remember, we have ingredients 1, 2, 3, 4. The first ingredient is to introduce a regularized algebraic decomposition of my strain energy density function. So what I'm going to do is that I'm going to take those small w's and I'm going to make them capital W's, just to denote the fact that those are just stochastic version of the other ones. And this is what I mean by an algebraic decomposition. I'm going to introduce this in such a way that the stochastic nonlinear boundary value problem is well posed most surely. And I don't want to basically, discuss the details of it. If you have questions, I'm more than happy to take you through the derivation of this. But the point I want to make is like, you cannot just take this guy and just randomize everything and run computations. The first step is that you need to make sure that you're going to satisfy this uniform coercivity requirement. The second step, if you remember that, is that we want to ensure we need to build a model, right? And to do that, I will need to use some information. So what I'm going to do is that I'm going to use information at small and finite strains. I'm going to take my strain energy density function, I'm going to linearize it, compute the small strain elasticity tensor, work out a little bit of this, and extract constraints that I'm going to use for my maximum entropy principle. Again, at this point, I don't want to do the mathematics of it, just, we do that. Now, the fourth ingredient is that how do I sample on this manifold? So now, one way to do it very efficiently is that if you remember, I have this H, and this H is how my vacuum, it's essentially setting the path my vacuum is going to take to filter the white noise. And to do that, we are using specific algorithms that are essentially going to define principal directions on the tissue. I don't know if you can see that on your screen because it's pretty dense, but essentially this is a vector field that essentially go in this direction, and this essentially goes in this circumferential direction. And once I have those two fields, I just take the cross product to get the through thickness direction. And once I have those two fields, I'm gonna filter the white noise according to this. So my filtering operator is just gonna follow my geometry on the fly. Okay, it's gonna just follow the flow. Now the first thing I'd like to show you beyond the mathematics is how it looks like when you compare the model with the experiments. So the black lines are basically the data set that we had. So we are using the maximum likelihood to calibrate the model. And what I do is that I'm using the model that I have right now, which has been calibrated, and I'm going to generate a confidence interval. And those are the red lines. This is the circumferential direction. This is the longitudinal direction. And so what you see is that basically, and the blue lines are basically the mean responses computed in two different ways. But that's a detail. And what you see that I can catch the variability on my data set very nicely. You may want to say that, okay, there are a few black lines which are out of this confidence interval. And this is simply because we didn't include this in the calibration process. If I want all the black lines to lie between the red lines, I can do it. I can design a cost function that can do that. But it's from a statistical standpoint, it's usually not the most robust way to do it. So this is for the first one of the layer, which is called the adventitia. And if you go if we go with another layer, which is the media, well, you see that this time all of my experiments are really nicely concentrated within my confidence interval. And this is something that I can use to run computations and see how the variability in my input is gonna propagate through my computational model. All right, and this is the last one. This is the intima. I would like you to appreciate the fact that if you look at those layers, the adventitia, the media, and the intima, they have very different stiffnesses. One are pretty soft, like this one is actually pretty soft. This one is actually pretty stiff, and this one is kind of in between. Okay. Nevertheless, the model can capture this very, very accurately. Now, once I have this, I want to run my computations on my domain, right? So now I'm going to combine my diffusion field, my fractional equation on my patient-specific geometry. And if you were to define this by hand, it's actually extremely difficult because the geometry is very complicated. But I'd like to show you it's how physics-based this model is indeed. So what I do, I would like you just to focus on this. So basically in my model, I have 3 parameters. And essentially tau1 and tau2 are going to control how much the information is correlated in space. And so what I'm going to do is that I'm going to fix the value tau1 is 0. And I'm just going to change tau2. So when I change tau2, basically, I'm going to say, well, I'm going to increase progressively how much correlation I have on my tissue. And when you look at this, you start from 1. So there is not that much, correlation in space. But when I increase this, 10 starts to look like highly correlated, and 100 is very, very, very correlated in space. But when I do that, it's actually very easy to interpret those results. Like I have 1 or 2 numbers, and if I look at my data, if I look at my simulations, I can quickly understand what's going on, and I can essentially quickly converge to set up my computations. There is just no way you could do that by hand, really. So we have very good modeling capabilities. We have a clear physical interpretation. We also have a highly computationally efficient framework. Everything I told you here, it looks complicated, but like running this on a mesh that has more than 1 million degrees of freedom takes a few seconds on my laptop. Right? So that's very, very efficient. So that we are truly talking about accounting for complex patient-specific geometry data on the fly in a reasonable amount of time. Now, this piece of artery is complicated, but it's small, right? If I were to simulate this on a much more like broader, like a larger domain, that would take more time. But still, it's very efficient. Now, I'd like to show you a bunch of uncertainty propagation results. So if you are not from computational mechanics, you may not be familiar with this, but when you are dealing with nonlinear elasticity in a computational setting, you need to account for this in a proper way. So we use something that is called the Hu-Washizu formulation, we have like more than 1 million degrees of freedom. It's implemented in Moose, which is like a finite element computing platform developed by Idaho National Labs. And boundary conditions are essentially sliding conditions on the boundaries and a pressure load inside. And I'm going to use a Monte Carlo solver to do statistics. And so here are a couple of results. So what I'm doing here is that I'm taking my geometry and I'm just sampling my model. So you could think about it as each plot would be the response of a different individual, okay? And you see that basically the combination, you see basically the interplay between the geometry and the material parameters. What you see that essentially the localization of the von Mises stress mostly depends on the geometry, which is kind of intuitive. But the magnitude of the fluctuations will depend on, of course, the mechanical parameters. But you could basically use that to make sure that you can design a clinical procedure or whatever you are interested in decision-making, accounting for the fact that you're going to have spread in your data. You can, and this is, I think, a very important message I'd like to deliver. Like you are really combining material uncertainties and patient-specific data. I'm going to stop here regarding the arteries, just to mention that we work on a lot of other biological tissues. We also work, like this is another example, we work on the spinal cord white matter just to test whether our stochastic hyperelastic models would work. So this is compression. So basically, you are reading this from the right to the left. So you go from this point and you go left, and you go from that point to the left. And basically, I'm just changing the compression rates. And essentially what you see is that the black lines are essentially the experimental data, the mean and the standard deviation. The red lines is essentially what the model is going to reproduce or predict. And the confidence region is the output of my stochastic model. So I can really augment my predictions with like spread, which is consistent with my experiments. And you see that those models, not only they are good from a computational standpoint, from a theoretical standpoint, but they can really truly mimic what you observe in the experiments. The last example I'd like to show you is also we did that for brain interfaces. So this is UQ for TMS simulations, where essentially we try to integrate the fact that we can get like some MRI segmentation errors, and this is something we would like to account for. So here, this is the figure on the left is the interface between, I think, the skull and the CSF. This is the interface between the CSF and the gray matter. So they're extremely complicated, right? I mean, if you look at this, if you were to define a stochastic process on this, defining the correlation function by hand, there's just no way you can do that. Again, we can do that on the fly very easily. And so we are randomizing this, accounting for input from MRIs. And then what we are doing is that we're going to look at how the electric field is going to be distributed on those interfaces. And here you see, like, this is a mean of the electric field, and this is a standard deviation. So using this, essentially, you can optimize your protocol and basically design, like, for instance, where you're going to put, the coil on top of the head, and you can really be predictive, just accounting for, combining the geometry of your patient, but also the fact that your MRI is not, can introduce some errors in it. Yeah. All right. Now, I was told that I could take like 50-55. So I'm just going to extend this just to show you, to discuss two other ideas that might be relevant to this audience. The first thing I would like to introduce is, in many cases, when you do computational mechanics, you basically assume that your model is accurate. So you assume that I have a couple of PDs, and my PD is the one I have to use. But there are many cases where this will never happen. Or there are cases where I have like a high fidelity PD, but I'm going to degrade the quality because I have, let's say, a strongly anisotropic tissue, nonlinear. But if I wanted to couple this with like a fluid structure interaction, it's going to take forever to run. And I'm mostly interested in the fluid part of it. So I'm going to degrade the quality of my model. But when I do that, I am introducing model uncertainties. I took my model, which essentially was accurate, and just turned it into like a simplified version of it. Or think about cases where my model is not perfectly known, or the model has to be discovered. Okay, so I'm gonna consider the setting where in my prediction, the P is gonna be known, but the model itself is unknown. So that's called model form uncertainties. So if you are familiar with that, there are essentially two common approaches to deal with this. One common approach is that, okay, if I have a bunch of models, I'm just going to run my computations for all of those models, and I'm just going to compute some average, weighted average. And I'm going to say that this is a prediction that is going to account for all those models. The other way to do that is basically to do model selection. And I would say, well, I have a bunch of model candidates. I have my data set, and I'm going to pick up the model that seems to reproduce my experiments accurately. Now, when you do that, what I would like to insist on is basically the fact that your prediction is going to be deterministic. You have a collection of models, but even if you have this collection of models, you're going to come up with a point prediction. And so we would like to go beyond that. We would like to say, well, if I'm doing mistakes, if I do reduced order modeling, when you do reduced order modeling, you're going to compress your model. You're going to introduce mistakes, errors. Can I account for this in a good mathematical way? I'm not going to, discuss this in details mathematically, but here is the idea. Assume that you have three models, okay? So I have three PDs. One is the high fidelity PD, and I have two low fidelity PDs. I'm going to compute a reduced order model, okay? That would be W1, W2, W3. Mathematically, they live on a manifold that is usually something that is called a Stephan manifold. But at this point, let's say they belong to a given space. So what I'm going to do is that I'm going to project those bases, those reduced order bases, into some tangent space, okay? So this tangent space is essentially a flat space. And the reason why I'm doing this is that if you are familiar with it, if you had a class in linear algebra, whenever you deal with a manifold, it's complicated because there is not a lot of things you can do on the manifold. But if you are on the flat space, it's much easier because that's a vector space. So you can mathematically you can manipulate object in a good way. And I'm gonna build a model on that space, and then I'm gonna project back. So I have PDs, I build reduced order models, I randomize on the tangent space, and then I can project back. That's the idea. And then if you look at how, and then I'm going to sample my models. So here's how it looks like. I'm calling this sampling and interpolating between models made easy, because essentially you assume that you have a bunch of models. One would be like fully hyperelastic, nonlinear, coupling everything, FSI, Navier-Stokes, whatever. So this guy costs a lot. This guy say, well, I'm gonna keep my Navier-Stokes, but I'm gonna simplify the mechanistic part of it. This one could be, well, I'm gonna simplify the Navier-Stokes, and so on. So I have those models, and what our framework allows you to do is basically to sample between those models and draw predictions that are essentially consistent with that collection of models. And based on that, then you can propagate this, and instead of adding 1 point prediction and just hoping that the model you picked up is the best, crossing your fingers, you say, no, I have a bunch of models, and I don't want to decide. Or I could decide, but on top of deciding, I'm gonna basically make sure that I can predict the confidence interval that is consistent with my setting. So this is kind of a new setting we are working on right now. We have a bunch of projects around this. And I think it's a nice setting to do, to basically do really like high fidelity computations. The other stuff I'd like to introduce very briefly is when you are trying to do deep learning stuff to model materials. So there is this huge push to have like everything data driven. And basically, if you look at how the hyperelastic response looks like, it looks like the basic idea would be, well, I could train a neural network to do that. So you could say, well, I'm gonna take this W and I'm going to approximate it by a neural network model. Well, the issue is that if you do that in a brute force way, you can run computations. Your neural network is going to return a lot of things, and you can go ahead with this. Now, there is just no way you can justify the well-posedness of what you did. And remember that at the end of the day, you're going to make decisions out of this. So you don't want to have something like a black box model that does something, but you cannot justify. So there is an issue here. So if you want to enforce admissibility, you can essentially restrict the neural network you are using. And people did that in the past. And basically, the easiest way to do that is basically you can constrain the weight and the activation function. Essentially, if you take positive weights and convex activation functions, then you can ensure polyconvexity. Right, so that's good. But the issue with this is that when you do that, because I'm looking at the subclass of neural networks, I have an issue about expressivity. And also because I'm doing this, because for instance, I'm going to restrict the space for the weights, it's going to have an impact on the training in the optimization. So we came up with this very simple idea to say, well, I don't want to touch the neural network. So the neural network is going to be like an unconstrained free neural network. But I'm going to introduce a sequence of transformations that are going to take this neural network that does whatever he wants to do and just shape it such that it's going to look like a polyconvex function. So if you take like a very simple isotropic model, like something like this, I'm going to assume like a simple additive decomposition. And the idea is that I'm going to express those strain energy density functions in terms of a neural network, but I'm going to apply some transformations on this neural network. And I'm not going to tell you how we do that because I think it's irrelevant. We are basically, there are two transformations. One is going to take your neural network and transform it into a non-decreasing function. And this is going to take a non-decreasing function and make it a convex function. So you take your neural net does what it does the best, just feed data. And you basically have a sequence of transformation that is just going to make it consistent with what you need. And we do that mathematically through integral transformation. So now we know that the model is correct. And now this is just to show you how it looks like when you apply this to experimental data on arteries. And as usual, that your neural net is going to be good at fitting data. But the point I would like to make is that not only we are fitting data, but I can guarantee that your neural network is good in terms of computation. So here you see like the response in the circumferential direction, and here along this axial direction. Okay. All right. So this brings me to my conclusion. So I've tried to do two things. So first of all, I spent quite a bit of time on introducing some of the stuff we did, like developing computational stochastic modeling frameworks for personalized medicine. And the key thing I'd like to say that when you want to basically introduce variability, the fact that when you have a population, like a set of patients, there is variability in it. You need to account for that in a good way. And actually, there are very few frameworks that will allow you to do that. As of now, most of the frameworks, of course, are focused on the geometry. So you take an MRI, you do classification, you get an STL, you mesh it, you run your computation. Now, what we are bringing here in is the material uncertainties across groups of patients. You can also do that on the fly using the algorithm that we have. And that truly, we believe, expand the range of predictive capabilities in computer-assisted medicine. So that was the main part of the talk. Then I just discussed very briefly two extensions. One is like, okay, usually I assume that my models are correct. I assume that my PDs are the correct ones, but it's not completely the case. You may have heard about model discovery right now, stuff like that. People are trying to refine or develop new models or a family of models. And then the second aspect I introduced is how about deep learning models? How do we make sure that those models, which are essentially designed primarily to feed data, they are not meant to be connected to computations, right? You need to make sure that they are essentially suitable for computation. How we did that in a simple case of constitutive modeling in hyperelasticity. Before we stop, I'd like to acknowledge financial support of various agencies, AERO, NSF, NIH, Sandia, the US NL. And just acknowledge once again the contribution of my group. And with this, I'm done. I'm happy to take any questions. Thank you.